Here the topic to be explained is series resonance. Series resonance. In the last video already I have derived impedance of that series resonance circuit at resonance is Q resistive or omega naught is equal to 1 by root over LC series resonance angular frequency omega naught, or F naught is equal to 1 by 2 pi root over LC. Geometric mean resonance frequency omega naught is equal to square root of omega 1 into omega 2. The resonance frequency is the geometric means of the two angular of our frequencies. Two of our angular frequencies omega 1 and omega 2. Bandwidth of the circuit is that means omega 2 minus omega 1 is equal to R by L. Another important is at resonance condition, the current is maximum, that is I naught is equal to Vm by R. I naught is equal to Vm by R. And also the net at resonance, the net voltage across the inductance and capacitance VL plus VC is equal to 0. All are explained clearly in part 1 video. Now I will concentrate on quality factor. Quality factor of that series resonant circuit. How the quality factor is related to bandwidth of the circuit. In this video, I am going to explain these things. Next, quality factor. Quality factor. Q naught, it is represented by Q naught. The magnitude of voltage, the magnitude of voltage across inductor or capacitor by voltage applied to the circuit. Voltage applied to the circuit. This one is the quality factor of the series resonance circuit. Suppose Q naught, consider inductance. Q naught is equal to mod VL by voltage applied to the circuit is mod V. At resonance, the magnitude of voltage across inductor or capacitor at resonance condition. VL is equal to mod VL is equal to, at resonance the current flow through the circuit is I naught, that is omega naught L. Generally VL is equal to I naught into J omega naught L at resonance. Mod VL is equal to magnitude, J term is cancelled, therefore I naught omega naught L. Mod V is, we know that V is equal to Vm sin omega t. Mod V is Vm only. This one is Vm. I naught is equal to Vm by R. We know that I naught is equal to Vm by R into omega naught L Vm. This Vm is cancelled. Therefore, quality factor of an inductor is Q naught is equal to omega naught L by R. Omega naught L by R. This one. Next, quality factor of the capacitor. Q naught is equal to mod Vc by mod V. Mod Vc means generally Vc at resonance, Vc is equal to I naught into minus J by omega naught C. Mod Vc is equal to J term is cancel. I naught by omega naught into C. Mod V is equal to Vm. I naught is equal to Vm by R. Omega naught C into Vm. Vm is cancel 1 by omega naught RC. Therefore, quality factor in for inductors Q naught is equal to omega naught L by R. Therefore, quality factor for capacitor Q naught is equal to 1 by omega naught RC. In the last video already I have derived bandwidth of the circuit is bandwidth R by L. Find out the relation between these two, quality factor and the bandwidth of that series resonance circuit. From this expression, Q naught is equal to, this one is omega naught L by R, omega naught R by L, that is equal to omega naught by R by L is bandwidth. Bandwidth is represented by B. Finally, Q naught is equal to, Q naught is quality factor of that circuit. Q naught is equal to omega naught. This one is omega naught by bandwidth of the series resonance circuit. Omega naught is 2 pi f naught. Bandwidth is omega 2 minus omega 1. 2 pi f naught by 2 pi f2 minus 2 pi f1. 2 pi cancel. Therefore, f naught by f2 minus f1. This is the quality factor. Consider this one. Consider this one. We will get the same result. Q naught is equal to resonance frequency by bandwidth of the circuit. Consider second equation here. Consider capacitance quality factor. Q naught is equal to 1 by omega naught RC. Q naught omega naught into RC is equal to 1. But bandwidth of the circuit is R by L. Numerator and denominator is multiplied with L. Q naught omega naught C L into R by L is equal to 1. Q naught omega naught into LC. R by L is bandwidth. We know that omega naught is equal to 1 by root LC. Omega naught square is equal to 1 by LC. LC is equal to 1 by omega naught square. Substitute LC is equal to 1 by omega naught square. Omega naught into 1 by omega naught square. Omega is cancelled. Therefore, Q is equal to omega naught by B. In both the cases, this case and this case, the quality factor is equal to ratio of resonance frequency to bandwidth of the circuit. Okay, next selectivity. Selectivity. The selectivity of a series resonance circuit is defined as the ratio of resonant angular frequency to bandwidth of the circuit. Q factor is nothing but the selectivity of the series resonance circuit. The selectivity of a series resonance circuit is defined as is defined as the ratio of resonant angular frequency to bandwidth of the circuit. Therefore, Q naught is equal to selectivity. Q naught is equal to selectivity is equal to omega naught by omega 2 minus omega 1. Omega naught means we know that F naught by F2 minus F1. This one selectivity curve. This one is a selectivity curve, omega mod I. Q here, Q is inversely proportional to bandwidth of the circuit. Q naught is inversely proportional to bandwidth of the circuit. Q is high value, bandwidth is low value. Suppose this one is mod I. One is I naught. Here half our points here is here omega naught, omega 1, omega 2. In this case, the band Q is very high. Q is very high. Selectivity is also sharp. In next case, here this one is omega 2 minus omega. Here bandwidth is more. This is the medium Q. Next one, coming to this one. More bandwidth. This one is omega 2 minus omega 1. This one is omega 2 minus omega 1 plus Q. Therefore, Q3 is greater than Q2 is greater than Q1. B1 is greater than B2 is greater than B3. This one is a bandwidth 3, bandwidth 2, bandwidth 1. For lower values of that Q, the selectivity of that series resonance circuit is pure. For higher value of Q, the selectivity of that series resonance circuit is good. The selectivity of an RLC series circuit is the ability of the circuit to respond to a certain frequencies. And discriminating against all other frequencies. The sharpness, this one is the sharpness. Some cases this one is not sharpness. The sharpness of the resonance in a resonance circuit is measured quantitatively by quality factor. That is called as a selectivity. That is called as the selectivity of the series resonance circuit. For better selectivity, the quality factor of that series resonance circuit is more. That is Q naught greater than or equal to 10. Q naught is greater than or equal to 10. One more next important derivation here is in the part A. In the part A, the net at resonance, the net reactance of that circuit is the net reactance of the circuit is resistive. Therefore, X is equal to plus or minus R at resonance. Already derived in part 1 video. That means omega L minus 1 by omega C is equal to plus or minus R. Here, omega square LC minus 1 is equal to plus or minus R omega C. LC is common term. Omega square by omega square minus 1 by LC plus or minus omega RC by LC. CC is cancelled. Therefore, this LC is the common term and bring back to this side. Omega square minus 1 by LC, this one. Okay. Omega square. Bring back this side, this term. Plus or minus means minus plus. Both are same. Omega R by L minus 1 by LC is equal to 0. This one is omega is equal to minus B plus or minus. Minus B means minus into plus, minus into minus plus. Therefore, as it is R by L plus or minus square root of B square. B square means R by L whole square minus 4A is 1, C is minus 1 by LC by 2 into 1. Therefore, omega is equal to plus or minus R by L plus or minus square root of R by L whole square plus 4 by LC. This term 2 is here and 2 is changed to 1 by 4 here, 1 by 4. 4 is cancelled. That is omega is equal to plus or minus R by 2L plus or minus square root of R by 2L whole square plus 1 by L. Two angular frequencies, half-hour frequencies are there on either side of the resonant frequency. That is omega 1 and omega 2 is greater than omega 1. Omega 2 is greater than omega naught. At omega 1 is this is the minus term minus R by 2L plus square root of R by 2L whole square. That omega 2 is equal to omega B is equal to R by 2L R by 2L square root of R by 2L whole square plus 1 by LC. See the two frequencies. Here omega 1 is equal to minus R by 2L. 1 by LC is the common term. R by 2L whole square 1 by LC plus 1. In that 1 by LC is the common term. That is equal to minus R by 2L. 1 by root LC is 1 by root LC into square root of Q is equal to Q naught is equal to W naught by bandwidth, omega naught by bandwidth. Bandwidth is equal to R by L. Bandwidth of that circuit is L by R by L. Already derived in the first expression. Bandwidth of that circuit R by L. Here R by L. R by L is the bandwidth by 2 whole square. 1 by, we know that omega naught is equal to 1 by root LC. Omega naught square is equal to 1 by LC. Here omega naught square plus 1. Therefore, omega 1 is equal to minus R by 2L plus omega naught B square by 4 Q naught square plus 1. That is equal to omega 1 is equal to minus R by 2L plus omega naught this one is 4 omega naught. B by omega naught by B, that is equal to 1 by 4 B by omega naught by B whole square plus 1 minus R by 2L plus omega naught 1 by 4 omega naught by B is the Q naught square plus 1. For large values of Q, Q is not is greater than or equal to 10. 1 by 4 Q naught square is neglected. Therefore, omega 1 is equal to minus R by L plus 2L plus omega naught. This term is neglected. Root 1 is 1. R by L is the bandwidth of the circuit. Therefore, omega 1 is equal to minus B by 2 plus omega naught is approximately. Similarly, omega 2 for omega 2 same action B by 2 plus omega naught. These are the omega 1 and omega 2 are the two half-power frequencies, angular frequencies, and either placed it on either side of the resonant frequencies. Half-power frequencies are for all practical purpose. These are the half-power frequencies for all practical purpose symmetrical around the resonant frequency. and can be approximated. With this, all derivations are completed for a series resonance circuit, part 1 and part 2 videos. Consider part 1 and part 2 videos. If you like this video, please subscribe the channel for further updates. Thank you.